Hello and welcome to another video. In this video we're going to be working on problems from the weekly contest 394, and this is also one of the easier contests, so we should be able to get through it pretty quickly. So let's get started. So the first problem, you're given a string word and a letter is called special if it appears both in lowercase and uppercase, and you want to return the number of special characters. So basically all we need to do is go through this thing, and also because there's only because if you think about it, first of all, the length is super short, but also, even if the word was super long, there's only 52 lowercase and uppercase characters, so we can just store the count of every character, and that's basically constant space. I guess we don't even need the count, technically, so I guess I could change this, but yeah, you actually don't need the count. You probably just need a set, and we could do that as well. So we can say, like, characters or something equals set word, and then this will be like this for keying chars, and this is fine because we don't really care about the count. We just care if it exists. And so basically we just go through every element and then we check. So I just use an ASCII table here. So uppercase characters are over here, lowercase characters are over here, and the uppercase version of a lowercase character is that character minus 32. So like A is 65, lowercase a is 97, and so on and so on. So basically we can just say for every character, if that character plus 32 is in our table, then that's another character that we have both upper and lowercase. So when you try this for an uppercase, you'll get the lowercase, and then if you try this for a lowercase, you'll just get an ASCII value way above it, and then like you'll never have those values. So then, this should just work. And it does, and so that's pretty simple. So you just have a set, and then you just check for every character. So this is how you, by the way, this is how you convert from character to other character. So basically we take our character, we get the ASCII value, we add 32, and then if that character is in here, so to convert that into a character, just use CHR. So essentially what happens is, like, if we have, let's say uppercase A, we'll convert that to lowercase, so we'll get 65 plus 32, we'll get this lowercase a, and then we'll say, like, yeah, it's in here, and then so on. And so for every uppercase character that the lowercase version is in our set, that's another one that we add to the result, and then we just return all that. So pretty straightforward. So let's take a look at B. Also pretty straightforward. So it's the same thing, they just have a small change. So they said return every character where all the lowercase occurrences, or the last lowercase or every lowercase occurrence appears before the first uppercase occurrence. So if you think about it, like if we just ignore all this, basically it's saying for every character, the last lowercase occurrence has to appear before the first uppercase occurrence. So pretty easy. All we do is just record for lowercase characters. We just record the location of the last one, and that's pretty easy to do. All we have to do is just every time we see a lowercase character, update its location, and then we'll only have the last one saved. And then for the uppercase character, we kind of do the opposite. So we only store the location of the first one we see, and then the rest we ignore. So like we'll store the location of this will be location 0, then we'll update that location to be location 1, then we'll store this location, this will be location 2, and so on. So you basically want to store the last location of the lowercase character and the first location of the uppercase character. And then the rest of it is very similar. So you just have locations. And then you can easily check if it's upper or lowercase. I didn't use like a built-in thing. I just calculate the ASCII value, so same thing. So if you look at this ASCII table, a lowercase character has an ASCII value of 97 and higher, and an uppercase is here. So if this is true, I guess I don't even need to use 90 here. So lowercase is 97 or higher. So I could use like 97. Or if you want to do it cleanly, you can do it this way too. Like this makes more sense instead of using a random number. So you could do it like this too. So if the ASCII value of the character is greater than or equal to the ASCII value of lowercase a, this is lowercase. And then all we need to do is just update the location with the last location stored. Otherwise, it's uppercase. And if it's uppercase, we only want to store the location of the first one. Then all we have to do is, for the same kind of thing as we did before, so for every single key in our locations, we just check like what's the uppercase version of that. You could do it the other way. So essentially when we get a key, we just subtract 32 from it. So like let's say we have A with some ASCII value, we'll subtract 32, And if it's an uppercase character, none of these will exist, so that will just fail. But if we have a lowercase a, we'll subtract 32 and we'll say, oh yeah, that's in our dictionary. And the location of the first uppercase character has to be greater than the last lowercase. And pretty easy to do that here. So you just say, okay, give me the uppercase character if the uppercase character and the lowercase character are both in our hash map, and the location of the lowercase character is less than the location of the uppercase character. We store the location of the last lowercase character and the first uppercase character, so that means every lowercase character comes before the last. So you don't need to store all locations, you just need the last location of each lowercase and the first location of each uppercase, and make sure that the lowercase comes first. Pretty easy as well. So both of these are like, I mean, this is like barely medium, I'd say. Just like basic ASCII values. Okay, so now let's go to the third one. So this one is a little bit tricky. It's not that bad either. I actually miscalculated the dimensions, but yeah. So essentially, you're given a 2D matrix of n by n, and you can change the value of any cell to a non-negative number. So basically, just the quick TLDR is you want every column, you want every integer in every column to be the same number. So like this column needs to be the same number, this needs to be the same number, this needs to be the same number, and so on. And adjacent columns can't be the same number. So in this first example, that's already the case, so we don't need to change anything, so we just return 0. In this example, so adjacent columns are the same number, and so, sorry, adjacent columns, every column has to be the same number, so that's not true. So what you could do is like one solution is like turn this into ones, then this would have to go into zeros, then this would have to be into ones. Now it wouldn't have to, right? But this is like you could turn it all into twos and like nines or something, but that would be more operations. So you could make this a little bit more efficient than what I made it, but really there's not. I'll talk about like what I did, but essentially because you can basically turn everything into one number, and the numbers are only 0 to 9. So you can basically just brute force figure out like, okay, if I turn this entire column into zeros, how many operations is that? And how do I do that? Well, all I have to do is for every column, just have a count of each number, right? And have a number of rows. So here I have 2 rows. Let's make this bigger. I don't know why this is this. So I have 2 rows. And if I have a count of each number, if I'm like, okay, if I want to turn all this into zeros, let's say, then it's just going to be the number of rows minus number of zeros. That's how much it costs to turn it all into zeros, right? Because I'll have some, so I have 1, so then it's going to be 1, and so on. So essentially, you can figure out how much it takes to turn the entire column into a number by just getting the total count of the rows in your table minus the number of that number that already exists. And from there, we can basically just kind of like do a brute force DP. So because these are 1,000 each, so m by n, like to go through our entire matrix. So what we can do is we can go through our entire matrix, and we can get, for each row, we can get a count of each value. So not for each row, for each column. So we'll have like a dictionary where it'll be like dictionary, column, and then we'll have a counter here. And the counter will just be like the count of each value. So it'll be like dictionary column, the number of zeros, dictionary of column, the number of ones, and so on and so on and so on. So we're just going to pre-compute this. And basically to go through the whole grid is m by n. So that's like 10 to the 6th, which is fine. And then we can just make a DP function. I didn't make this like bottom-up space optimized because I've done it enough. I don't need to do it. But essentially, if you think about it, what do we need to do for a DP function? Like if we want to, basically our choices are to convert each column to 0 through 9. So in order to do that, like what information do we need? Well, the thing that it tells us is we need to convert the entire column to one number, and then adjacent columns can't be the same number. So all we need is we need a column that we're on and a last column number we want to call it or something. So like in this, let's say we want to convert our first column to ones. So when we first call this function, our column will be 0, and then our last column number, maybe we can pass like -1 or something, because we can use anything from 0 to 9. But essentially, in your DP function, you'll just say like, okay, let's try to convert it to zeros, ones, twos, whatever. You might need to convert it to. You can't do a greedy for sure, Like there's definite use cases against a greedy. Like I was thinking about this one. So like here's a pretty easy example that you can't just like convert everything to the most frequent number. So let's say this is like this. And the second column is like this. If you did a greedy, you would convert everything into zeros, which would be 3 operations. And now you can't convert this into zeros, so you would convert it into ones. So this would be 4 operations. So this would be 7. But it's better to convert the first column into something that's not a zero. So let's say we convert it into ones. That's 4 operations. And now we can convert this into zeros, which is just 1 operation. So it's pretty easy to disprove greedy. You can just think of like some stuff. And then once you know it's not greedy, you can optimize it a little, but because you can only convert, like you only need to check 0 through 9, like realistically what you can do to optimize it a little is basically, yeah, you can't do greedy, but it's going to be like 2 to 3 things that you have to check because you just need adjacent columns to not be the same. So here, you're never going to convert everything into like a 4, for instance. Like that's never going to be the case. Because if this is like, let's say the optimal solution, this has to be zeros. In this case, this just has to not be zero. So there's only like a few things you have to try for, and so on and so on. So you can like optimize it a little, but there's no need. So basically the idea is we just have a DP function where we store the current column we're on, and then the column of the last thing. So like if we say like, okay, let's turn the entire column to ones, we're going to have a count here, so we don't need to like loop through this whole thing. We can just do this in O1 of like how many operations it takes to turn the whole column into a number by storing it in a dictionary. So let's say we want to turn it all into ones. That will take 1 operation plus dp of the next column, which is 1, and the last number we use, which is 1. And then when we loop, when we try to turn this column into 0 through 9, we can't turn it into ones because 1's already taken. So let's take a look at the code for that. Pretty straightforward as well. Here it is. And like I said, I'll talk about space optimizing as well. So you get rows and columns, you get a count for every column, and then basically for every column I just made a dictionary. And so yeah, for every column you just make a dictionary, and then for every single cell you just increase the number of that thing. So we can actually print it, just to show you. If we print counts here. So for this column, for example, we can look at the picture to make it easier as well. So for this column, column 0 has 2 1s, column 1 has 2 zeros, column 2 has 2 2s. Like for example, column 1 has 1 0 1 1, column 0 has 1 0 1 1, column 2 has 1 and 1, and so on and so on and so on. So you basically get this thing, then you do a pretty simple DP. So the DP is just what column you're on and the last number you picked. So if you're on the last column, like if you're out of bounds, you just return 0 because you're done. You initialize the result to infinity, and we just try every single number 0 through 9. And we make sure that we don't use the same number we used last time. So if we try the number that we had last time, we just skip that one. But otherwise, pretty easy. It's just going to be the number of rows minus the count of the current value you're trying to convert to is going to be how many operations it takes, plus dp of going to the next column and whatever value you picked. And then I just initialize it to column 0 and the last number -1 just to make sure that I could try 0 through 9. Like I said, you can space optimize this to get rid of this because every recursive call goes into the next column, which you can space optimize to make it faster. But this is fine too. So I didn't space optimize it because I've done this like a billion times, so not super important. And so yeah, I think it'll be faster if you do space optimize, but not a big deal. I'm more focusing on like finishing problems and like the actual solutions and stuff, not like doing, it's kind of like coding union find 500 times. Like I'll code it 1 out of 10 times or something just to make sure I can remember how. Okay, so the last one. So there's like a little bit of trick to the last one, and once you get the trick, it's pretty easy. So, and I'm assuming you can use like, if you're doing these problems, I'm assuming you can do like jigsters and all that stuff. I'm not going to like go over that here. That's going to be for like a medium problem for jigsters. I'll go over that in more detail. But essentially, you're given a undirected weighted graph from 0 to n minus 1. And and there's m edges, and so just pretty basic graph. And you want to consider all the shortest path from 0 to n minus 1. So you need to find a Boolean array. So let's actually go through this in Excel draw so I can like draw the shortest path to be easier. Get rid of all of this, and I have it up here. So let's go through it here and make all this bigger. That way we could draw it all so it's a little bit cleaner. But yeah, basically you have a graph undirected with weighted edges, and you want to consider all the shortest path from 0 to n minus 1. Let's do this. This is here. And also, if you take a look, you have 5 times 10 to the 4 nodes, so like an n squared solution or something won't work. So yeah, you have all that. You want to consider all the shortest path. You want to find a Boolean array where answer is true for the edge, if the edge is part of at least one shortest path. So this is where it's a little bit tricky. So what Jigsters does is it guarantees to get you like a shortest path, but it won't give you all of them. Like if you use Jigsters with a heap and a visited set, you'll get a shortest path. So like here, in this first example, the shortest path looks like it's 5. So like this is one of them. This is another one. Let's just draw them all out. So like this one. I think there's a couple more. So there's like, I guess let's draw them in different colors actually to make it easier to see. So this is one. This is one. Then there's another one here. So a little bit hard to see, but it's like this. Right, so 2, 4, 5. So I think that's all of them. And then basically, so all of the edges that aren't this edge and this edge, you should return true for. So if you look at the edges, 0, 1 should be true. 0, 2 should be, basically every edge other than 1, 4 and 4, 5 should be true. So if we take a look, the one that's false is 4, 5 and 1, 4 if there's a 1, 4, yeah. And the way to do this is, I don't know if it's doable with just like, if you just do a Jigsters from the start, like I was thinking do a Jigsters from the start, and basically the idea would be like you have a visited set, but instead of just saying it visited, you visit and then you record how far it took to get there. And then if it took the same amount, like let's say I get from 0 to 3, and then I get from 0 to 3 again, well, I might have gotten there a different way, right? Like for example, like let's say I go here, this is 4, this is also 4. And you want to record both of these. So the idea would be something like when you get to an edge, check how long it took, like what was the shortest path. If I never got there, obviously record this path. But if the path here is the same as it was before, then record that too. But the problem with that is you'd have to store like the distance and then the whole path for every path, which would be kind of like not great. So the trick to this problem is basically what you want to do is you don't want to store like the whole path, but you want to recognize like what it takes for an edge to be in the shortest path. So if an edge is in the shortest path, there's basically one of two, like you can recognize that for an edge to be in the shortest path, you're never going to traverse an edge more than once, right? It wouldn't make sense. Like if I traverse this edge and this is part of the shortest path, I'm never traversing it twice. I'm never going to like do this and then like loop through it again. So you're only going to traverse an edge once in this unweighted graph. You're never going to traverse it more than twice. So more than once. So basically, if an edge is in the shortest path, there's two scenarios. You either go from 0 to like let's call our edge like xy, right? You either go from 0 to x to y to the end, or you go from 0 to y to x to the end, right? So like if this edge is part of it, I'm either going to go from 0 to the left part then to the end, which I am, or I'm going to go from 0 to the right part in some way and then to the end, right? One of those, and that's always going to be true. So if you know that, that's kind of like the trick to this problem, that if I do use an edge, I'm either going to go from 0 to x, then traverse the edge, then go to the end, or the other way. And if you know that, you can basically just do Dijkstra's from 0 to every node, right? So we can make a graph. We can do Dijkstra's from 0 to every node. That part should be pretty straightforward. That's just straightforward Dijkstra's. Like there's nothing like a multi. You just do a heap, and then you just keep traversing the heap until you visited everything you could. And then you're gonna have a dictionary of like shortest path from 0 to every node. Then you can do the same thing from this end node. So shortest path from end to every node. Yeah, so let's get rid of this. Then basically for an edge, like let's say our shortest path here is so our shortest path here is 5, right? So this is our shortest path. So when you do this, by the way, when like 0 and the last node might not be connected. So we can actually get rid of this. So 0 and the last node might not be connected, and when you run Dijkstra's from 0, like if you never get here, then you just return all falses, right? So if 0 and or start and end, we'll call it not connected, like I wasn't able to find a shortest path, return all falses. So, and you can just check for that here. If that's the case, you just don't even have to do anything else. So if they are connected, then you do this. Then for every single edge, so let's actually just walk through our edges. Let's maybe somehow, yeah, let's move this, make it smaller and stuff, and move it up here. Okay. So here's our edges. So our shortest path is 5. Then for all of our edges, basically, like I said, you either go start x, y, end, or you go start y, x, end. And because you know that, we have our shortest path, right? So this start x is just shortest path from start to x, and start y, shortest path from start to y. Then and then y end is shortest path from end to y, x end shortest path from end to x, and xy is just the weight of the actual edge. So basically you can just check, does this equal the shortest path, or does this equal the shortest path? And if one of those is the case, then your edge is on the shortest path. So we can walk through that. So 0 to 1, so this edge here. So 0 to 1, so let's try the first case. Let's try both the cases, right? So we'll have our first case and our second case. And our thing is 5. So our first case is start x, y, end. So which means we go from 0 to 1 and then from 1 to the end. So 0 to 1 is just, so we can take a look. So 0 to 1, so it's 4 this way. What other path is there? It's also 4 this way. So shortest path from 0 to 1 is 4, right? And then from 1 to the end, shortest path is just this one here. So, yeah. Actually, sorry, I did this a little bit wrong. So, so we need to do start x, right? So start x is just the path from 0 to 0 because x is 0. So start x is 0, and then the weight of the edge 0 to 1 is 4, and then the weight of 1 to 5 is 1. So because this is 5, that means this edge is on the shortest path, and we don't even have to try number 2. So we're done there. So this first one is true. Then 0 to 2, so same thing. Let's try x being 0, which is just 0. Start x is just 0, 0 to 0. Then 0 to 2, the weight is 1. And then 2 to 5, what's the shortest path here? So it looks like it's 4. No, it's actually, yeah, it is 4. So that, and which is 5. So 0 to 2 has to be on the shortest path as well. So 1 to 3. So this is the one where we have to do start x. So 1 to 3 first, we have to try 0 to 1. So 0 to 1, the shortest path is 4. 1 to 3, the weight is 2. And then obviously this is going to be bigger than 5, so that doesn't work. So if 1 to 3 doesn't work, then we have to try it the other way. So we have to try 5 to 3 to 1, because that might work. So 5 to 3, the shortest path is 3. And then 3 to 1, it's 2. And then 1 to 0 is still too big. So this is not going to work. So this one should be false. So 1 to 3 should be false, I believe. Oh, it's actually true. I think I screwed something up here. Let's see. Oh, right. Yeah, I did screw it up. So 1 to 3 actually, yeah, so I screwed up. So the path we want is this second one, right? We want start y, x, end. This will work because 0 to, yeah, so if it's this 1, 3, 2 path, or this 1, 3, 2 edge, so we can go 0 to 2, which takes, or 0 to 3, which will give us 2, and then 3 to 1, which will be 2 more, and then 1 to 5, which will give us 1. So this is true because that's 5. So the first one wasn't true, like this star x, y, end isn't true, because we can't go this way, but we can go this way. That's why you have to try both. So this one is true, then 1, 4, so we can try 0 to 1. So 0 to 1 is 4. Then the actual path from 1 to 4 is 4, so that way is too big. Then we have to try the other way, so start y, x, end. So we have to try 0 to 4, which is obviously going to be too big because 4 is like way too far. So this one will be false. And so this is the fourth one, so this is false. Then 1, 5, so 0 to 1 is going to be 4, and then 1, 5 is going to be, or the actual edge will be 1, and then 5 to 5 will be 0. So that part is true. And then 2, 3, so we can try 0 to 2 to 3 to 5. So 0 to 2 is 1, 2 to 3, the actual edge is 1, and then 3 to 5 is shortest path is 3. So this is 5, so that one's true. 3, 5, so we'll try 0 to 3 first. So 0 to 3 is 2, and then the actual edge is 3, and then 5 to 5 is 0, so that one is true. And then 4, 5 is the last one, so we'll try 0 to 4. So 0 to 4 is way too long, and then we could also try 0 to 5 to 4 to 5, which will be too long, right? So basically it would be like 0 to 5 to 4 to 5, which will be obviously not going to work. So yeah. And obviously, that's obviously not going to be on the shortest path, right? Because why would you go from 0 to 5 to 4 to 5? It doesn't make any sense. So you're either going to go 0 to 4 to 5, or this one will never work unless 5 to 4 is length 0, because 0 to 5 is already at the end. So those two are false, and the rest are true. So basically, that's the idea: is you do jigsters from the start node and from the end node, and then one of these two cases has to be true for the node to be in the shortest path, and that's what you have to recognize. So let's take a look at the code. Code, pretty straightforward. So you make the graph. And then I have two shortest path like dictionaries. So this is from 0 and this is from the last node. And then I just initialize everything to false. I make a jigster function because it's the same exact thing from 0 and from n-1. So I make a heap, visited, set, all the standard jigsters. Not really going to talk about that in detail. And then basically, yeah. So you just pass in one of these. And so this is going to be the dictionary of distances from 0 to every node. And this is going to be the distances from n-1 to every node. You run that both, and then, like I said, once you run jigster from 0, if you couldn't go from 0 to the last node, then the first and last node aren't connected, so everything is false, return false. Then you run jigster from the last node, and then you just go through all the edges. So if x is not in from 0, or y is not in from 0, or like basically if these things aren't, like, I think maybe you don't even need all these edge cases, but essentially, if these things aren't true, then there is no like path at all. So, for example, like let's say we have, like let's say we have some extreme case like 0, and then let's say we have like our last node, we'll call this L, and then we have like 1, 2 over here. So if there is no path from here to here, or from here to here, or from here to here, or from here to here, I guess technically what you could check is just these two. So if there is a path from these two, like this, because, you know, these are connected, there will always be a path to the end, so you can probably save this. That's not necessary. So essentially, If x and y are connected to 0, that means there's always going to be a path to the end somehow. But if they're not, then there's like no point in even checking for the shortest path, because there is no shortest path from 0 to going through these. Like if these aren't connected to 0, that means these can't be on the shortest path because they're not even connected to the thing. So anyway, and then you just check the two cases. So if from 0 to x to the plus the weight of the edge plus from y to the end, or from the end to x plus the weight of the edge plus from x to 0, one of these has to equal the shortest path. So if one of these does equal the shortest path, and the shortest path is just let's see, oh yeah, this is the shortest path, right? Shortest path is just the shortest path from 0 to the last node. One of these has to equal to it. If it's true, then this edge is part of one of the shortest paths, and then you should return it. So pretty simple. Once you realize the trick to not store the entire path, once you realize the trick that in order for an edge to be on the shortest path, I can just calculate it in O of 1 once I have jigsters from the start and the end, instead of like maintaining a path and making it super complicated. This is like 10 times easier once you realize it. Yeah, and then as far as like time complexity and all that, it's the same as just the regular jigsters, which I always get wrong, so I don't want to talk about it. But yeah, it's like v plus e plus something. It's like kind of yeah, I don't know. Definitely it should. I think the problem is every time I look up time complexity for jigsters, every other solution gives me like a different time complexity, so it's kind of annoying. So I just choose to ignore it most of the time, or I can like briefly talk about it if I need to in an interview. But yeah. But yeah, so this contest definitely one of the way more doable ones. Like I think the first two problems were super easy. This one pretty easy, I want to say, and then the last one, if you just see kind of the trick, then once you know the trick, like if you like watch this video and you see the trick, then the code part of it is obviously like just coding up jigsters is like a medium. So. But the trick is kind of not super easy to see, so I'm not sure where I would say that. But yeah, there have been, to be honest, like I think at least half of the hard problems in the contest, like even if you know what to do, there's still a ton of code. This one, not the case. If you know what to do, it's pretty easy. So yeah, hopefully this was helpful. If it was, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.